So, okay, good. So I have been given the task of discussing about, so I hope this is clear, the font size. So if I'm writing too small, you can stop me. So I've been given the task of discussing periodically driven quantum systems. This is a very broad topic, so I'll only cover some aspects of it, also because I don't understand all of it myself. So, yeah. Okay, so, but I'll stress on some open questions also when I reach that point. Okay, and needless to say, if something is unclear, you should stop me at that point, not wait till the end of the lecture. And it's good to have a discussion, and I'll try to clarify if there's some confusion to the best of my abilities. Okay? So in today's lecture, I'll discuss something which you might have heard about last time from Leah Santos's lecture, which is this eigenstate thermalization hypothesis. Basically, what I'll discuss is its generalization to this kind of a setup. And so this lecture would be sort of a broad lecture. It won't have some very specific models. But in the subsequent lectures, we'll of course discuss some very specific examples. Okay? So needless to say, there might be some overlap with what you have heard already from Leah's lectures. And there might also be some overlap with what you will hear in Subrata Mukherjee's lectures, but the overlap won't be too much. And it's always good to hear the same thing from slightly different perspectives. Okay? So, yeah. Okay. So I don't think the overlap would sort of be there from the second lecture onward, but in today's lecture, there might be some things in common. Okay, so what is the setup that I have in mind? So we are primarily going to discuss isolated many-body quantum systems. And we are going to, let's say for concreteness, discuss systems which are living on a lattice, not in continuum, okay? So this is the concrete setup. So we'll discuss lattice models of fermions or spins or hardcore bosons with which are interacting through a local Hamiltonian. So they don't have necessarily long-range interactions. There are some short-range Hamiltonians. So you see here, I have written fermions or spins or hardcore bosons and not just bosons, because I also want to concentrate on physical situations where the local Hilbert space is finite. Okay? Because in principle, if you have bosons, the boson number can run from anything from 0 to infinity. Right? So in that case, the local Hilbert space is not finite. And of course, that's also a very interesting case. But for what I'll discuss in this lecture and in the subsequent lecture, it's easier for me to have this demarcation of finite local Hilbert spaces. Okay? So, right. And in this setup, what we'll do is start with some initial pure state and drive it unitarily. So it's really driving through some quantum mechanical rules, okay, and there is no external heat path. So this is a purely unitary process. This is important, okay, this is a purely unitary process. Of course, there are various interesting questions about what happens when you couple these periodically driven quantum systems to, let's say, open baths. But because I have only 5 lectures and I only want to cover certain things, I won't cover that aspect. Okay, so in these set of lectures, we'll only consider problems like this, which are driven through purely unitary dynamics. Okay, so if you start with a pure state at time 0, you are always in a pure state at any time t, okay? So that's the setup, okay? So of course, I mean, from a foundational point of view, this setup is nice, but you might think that this is too artificial if you think of experiments. But as most of you are perhaps well aware, for the past 2 decades, there have been some fantastic experimental platforms where this thing is valid to a very good approximation for reasonable time scales, okay? So just to give you some examples, so for example, ultra cold atoms, superconducting qubits, then trapped ions, and so on. And there are some other examples, okay? So possibly, in the last week, you have heard of situations where there was no time dependence in the problem, no time dependence in your Hamiltonian. So your Hamiltonian is some given Hamiltonian like this, some many-body Hamiltonian like this. And then, of course, it's very easy to write what this unitary evolution is. Okay. So often I'll just take h bar equal to 1. So just excuse me for that, right? So this is what we are very familiar with, and you must have heard about what happens in some of these situations last week, okay? So what we are also going to concentrate on is what happens if you generalize this problem in a certain way. So see, of course you can say that, let me go from this static situation to a situation where there's an arbitrary time dependence in the Hamiltonian. But that's a very complicated situation, and you lose you lose all sense of solvability in some sense. I mean, you cannot then generalize this structure here in any obvious manner, okay? So one interesting case where some aspects of this structure generalizes here is actually this case, where you are not dealing with a static Hamiltonian, but you're in fact dealing with a Hamiltonian where there is some parameter in that Hamiltonian that is periodically driven in time. Okay, so that's the meaning of this notation. So this t is the time period of that parameter. So for example, if you consider quantum spins, then for the quantum spins, you might have some interspin coupling described by some Heisenberg interaction, and you might have some magnetic field which couples to the spins. And let's say you're driving that magnetic field as some periodic function in time. Then of course that's one realization of this kind of a process, right? So this capital T is in the hands of the experimentalist, right? So that's some external tuning parameter, okay? So this is an example of what is known as a Floquet problem, right? So because Floquet was looking even before Bloch about things which have certain kinds of periodicities, more specifically periodicities in time. Okay, so the quantum mechanical problem concerned with that. Okay, so of course when this is time periodic, it's not so easy to write this unitary evolution. But suppose I want to write this unitary evolution for one time period. So for one full cycle or for one time period, then basically I need some time ordering here. And I need this time ordering here specifically because of the fact that in quantum mechanics, it's not generally true that in such a driven problem, that the Hamiltonian at two different instances of time commute with each other. So because the Hamiltonian at two different instances of time does not commute with each other, you of course need this time ordering here, right? Okay, so that's standard quantum mechanics. Good. Now it'll turn out that this problem has some superficial similarities to this problem, but it has some extremely important differences as well. So it's good to have a sense of both these things. Okay? So again, interrupt me if something is not clear. Okay?
So
yes?
This question might not be like contact him of the legacy, but you said that in these experimental platforms, if I start from a pure state, it will be for a pure state for a very long time, right? My question is that so can you tell me physically like why in an experimental system the pure state becomes a mixed state? Like because the classical probabilities why it comes?
No, because even in these ultra cold atoms or superconducting qubits and all, there's always a bath. There's always an external world. If there's no external world, then of course the experimentalist cannot access the experiment, right? It's just that the coupling to the bath is very small, so that gives you a large time scale beyond which it's important to take the external bath into account. See, no real problem in physics can ever be exactly solved. Okay, so you have to make all levels of approximation. This is one level of approximation. Okay, yeah. By the way, this was not a joke, it's a true statement. No problem in physics can be exactly solved. So, yeah. Okay. Good. So now, let me first give you a very quick recap of what happens in this case. And this will quickly, I'll just be very brief about it because I have the impression that Leah already discussed some aspects of eigenstate thermalization hypothesis. But I'll be very quick and I'll sort of again belabor the important points from my perspective and then I'll generalize it to Floquet ETH. Okay, good.
But she was looking at it from the random matrix.
Oh, I see. Okay, so then maybe it's not, okay, I see. So I'll go on. Of course, if you guys think certain things are worth addressing in more detail, I'll be happy to do that.
Why are you particularly interested in like systems which are always in pure state? Because it's quite particular.
Well, okay, there are two reasons for it. Even if you take a mixed density matrix, if you understand what's happening for the pure states really well, you can actually answer the question for mixed density matrices as well, as long as the mixed density matrices are also propagating just with the equation of motion like this. You understand? The situation is different, so that's part one of your question. The situation is different if you have an external bath connected to the system. Then the dynamics is not unitary. Then there are sort of, actually then it's quite a big open problem. Then one way of doing it is through something called Lindblad equations, but that also has its own limitations. But yeah, the first part, the simplest answer to your question is if you understand what's happening at the level of these pure states, they provide you with a basis of expanding any density matrix and then you're done, as long as the dynamics is unitary. Okay? The second question about what happens if you have a non-unitary dynamics is of course beyond the purview of what I'm going to discuss. Okay? Any more questions? Okay. So because this might not be a recap technically, so I'll just put so it's actually very interesting to note. See, here it's all unitary dynamics and quantum mechanics, and there's no thermal bath attached to this setup, right? But it's very interesting to note that in some very interesting ways, statistical mechanics emerges from this picture. Okay, so in what way does it emerge? And that's the content of the eigenstate thermalization hypothesis. So let's just see that. Suppose you looked at a lattice model with a sufficiently complicated local Hamiltonian. Well, by sufficiently complicated, I just mean it should be a reasonable interacting system. Okay? And you start with some reasonable initial state. I'll be more precise about this term, reasonable initial state. And you look at a class of reasonable operators, and I'll be more precise about what reasonable operators are. then you will see that there's a natural way in which statistical mechanics emerges when we follow the time evolution of such a system. So what do I mean by that? So what I mean by that is, so this wave function is time evolving, right, through some unitary dynamics, which in the static Hamiltonian case is just e to the minus ish t. If you look at expectation values of certain operators, and I'll define what these operators are, so you can just write it as O of t as well. Then, suppose you start from initial states. Suppose you start from initial states such that, suppose you start from different initial states. So let's say this initial state, that initial state, and so on. Suppose you start from different initial states which have the same conserved average energy, then what you will see, and the other symmetries being equivalent, I'll come to that point later, because your Hamiltonian might have many symmetries apart from just energy conservation, then what you'll see is that if you follow this, let's say this is initial state 1, you might see something like this as a function of time for a macroscopic system. If it's initial state 2, you might see something like that. Of course, I'm drawing a schematic. If it's initial state 3, you might see something like this. In fact, there's a class of initial states here which are very interesting, which are these. And actually, you can guess it, what these initial states are. Can you guess from quantum mechanics what these initial states are? Eigenstates of the energy, right? But you see, now there's something very interesting here. So I'm claiming that if you see the temporal evolution of certain operators, and I'll come to what those operators are, then you see that after a certain amount of time, the system seems to lose memory of its initial condition, right? Because at time t equal to 0, you could distinguish these initial states by the expectation value of these operators. But if you wait sufficiently long in time, through this evolution, unitary evolution, that information seems to be washed out. Of course, that information is actually there. It's just getting transferred into some extremely complicated quantum correlators that you can never probe through simple operators. That's exactly what's happening. Okay? And what does this t equal to order 1 imply? It implies that typically this time scale, which you can imagine as a relaxation time scale, typically this time scale does not scale with system size n when it is very large. That's what I mean. Okay? Yeah?
I'm slightly confused.
Yes?
You initially told that these states that you choose have the same expectation value at time 0.
No, only for the operator h, not for all operators.
So, all right. Here it's a general operator.
Of course, exactly. Of course, if I took the operator h here, then this diagram is very trivial. Can you tell me what this diagram is?
It's just all of them are coming from the same point, right?
No, not just that. They're staying the same. Because energy is a conserved quantity of this, this unitary dynamics, right? So it's a very trivial thing. So you have to see something more non-trivial. Okay, so yeah. But this is pretty cool. This somehow seems to indicate that there's some notion of thermalization even from pure unitary dynamics. Yeah?
So when they reach that steady value, so the fluctuation around it, does it depend on state to state, or do you have a general understanding of what is the fluctuation, order of fluctuation?
Yeah, so if you calculate the fluctuations correctly, the fluctuations would again go as 1 by square root n, and their coefficients would give you response functions.
And does
Yeah.
it depend on state to state?
There is some statistical fluctuation on top of this statement, but they are extremely subdominant compared to the main part. Yeah.
So by system size, do you mean the
No,
Hilbert space?
no, the number of degrees of freedom.
Number of degrees.
Yeah. N denotes the number of degrees of freedom. Of course, the Hilbert space scales exponentially in n. Okay? Yeah.
And then eventually there will be a recurrence, which is very, very, very
Yeah.
long time.
That time scale would also scale as exponential of n if this theory is non-integrable, and it will scale polynomially in n if the theory is integrable. You can see I'm waving my hands because I haven't defined these things for you. But in a generic theory, it's exponential of n, which is a huge time scale. So it's practically irrelevant if n is large, right? So, yeah. But by the way, even that recurrence is what is called as a weak recurrence. So there's some interesting, but let me not discuss it here.
So it's not probably revisiting the initial state.
No, it won't.
Just
No.
In terms of this operator,
Yeah,
coming
yeah.
back to its initial value. So in that sense,
Yeah, yeah.
So it's not related to the classical Poincare recurrence theorem.
I think in this quantum setup, there is a softer version of it.
no,
Yeah.
I don't think it is, because
Yeah.
that is like revisiting exactly.
Yeah,
the
yeah,
initial state.
yeah. Okay,
But there is a paper, right, by.
sorry, yeah.
Yeah, so but there is a paper, right, by Boscheri in 1959. It's a PRM paper where they prove that there is a Poincare recurrence theorem in quantum domain, as long as you consider your dimensionality of the universe.
But what objects do they look at? Do they look at this expectation value of local operators?
The states only.
Okay, so maybe it is, okay. So what I know numerically that happens is that there is some time scale like this which scales in this manner, after which there is some weak revivals in these things. But maybe there's an even longer time scale when this happens. Yeah. Yeah, to me the first time scale was already very long, so yeah, okay, good. So so when does this happen? So as I said, one important thing is H is local in real space. Second thing is this psi, initial psi, is typically, so imagine a spin system, for example. So typically it's some simple wave function like this. So these are what are known as unentangled wave functions, right? So this is typically the case in an experiment or in a simple setup, right? So you might think that, okay, there are n block spheres. Suppose you're thinking of spin half problems, right? So there are n spin halves. So each spin half has its block sphere, and you can just initialize each spin to be somewhere on its block sphere, and you can just tensor product this, and that's a many-body wave function, right? So that's one possible many-body wave function.
So Arnab,
Yeah.
this local just means that if I concentrate on one lattice site, the spin degree of freedom residing on that site interacts at most with a finite number of other.
Yeah, exactly. So let me be more precise. So what I'm imagining is, suppose you have one spin here, it at most interacts with k spins, which can be localized in a box around it, and that box is finite when you scale the system size to infinity.
I keep this one fixed and
Exactly.
the outside,
Yeah. Right. So you don't scale this one, but you can scale that one. Yeah. Okay. So actually, just for completeness, this is you can start with states which are more complicated than this. I'll be very brief about this. So strictly speaking, you can start with an initial state whose average energy scales extensively. Okay. That's a reasonable thing to do because you want to ultimately do thermodynamics or statistical mechanics, right? So that's one thing. And the second thing is that the fluctuations of this quantity, right? Because this is not an eigenstate of the theory in general, right? So of course energy will have some fluctuations in the state. So those fluctuations which you can define again by calculating h square expectation value and subtracting h square and taking a square root given this initial state. This fluctuation should be sub-extensive. So typically these fluctuations grow as order square root n or smaller. So actually most reasonable states that you can prepare for short range interacting systems would have this property. This is a consequence of the central limit theorem for short range interacting systems, this thing. So it's a reasonably general setup. Okay, good. Of course, eigenstates also satisfy this property because if you take an eigenstate somewhere in the middle of the spectrum, its energy is extensive. Also, there's zero fluctuation in its energy, right? Because it's an eigenstate, right? So you know its energy precisely. Okay?
So like, I don't know, why is it that if I choose a state in the middle of the spectrum, I understand the first statement will hold, namely the energy expectation will scale. But why, like, is it obvious that the fluctuation would scale as square root of n for an eigenstate?
No, for an eigenstate, for any eigenstate, it'll actually be zero, the fluctuation.
So
See,
something middle of the spectrum for n.
oh, no. I said that in the middle of the spectrum, this property is obviously true, and the second property is also obviously true because the fluctuation is precisely zero.
Okay.
See, what did I say here? Order square root n or smaller. So it's precisely zero, so it anyway satisfies this property. Right? So actually, if some state does not satisfy this property, then you can actually show that that state would not give this. Okay? Right. Anyway, let me not go into that now. Most states satisfy this property. Okay, then comes the third thing, class of operators that thermalize. So what are these O's on a lattice system? So actually, these O's are, so let me just draw some 1D lattice for simplicity, are what are known as local operators. So you can see all the time that this sense of locality is very important in all this. So for example, again, if you have a lattice site, suppose you think of an operator which can be localized in a few number of sites, right? It may be a complicated operator or a simple operator. Suppose you think of a simple operator. Maybe you're measuring the magnetization of a site for a spin half degree of freedom, right? So that's a simple operator. Maybe you're looking at some correlation function. Then maybe you're looking at some nearest neighbor correlation function. Maybe like this. Maybe you're looking at something more complicated, whatever. But as long as you can localize the operator in some finite patch in real space, which again does not grow as you take the system to infinite size, then that's a local operator. So all local operators satisfy this property. In fact, sums of all local operators also satisfy this property. Okay, so for example, if you didn't look at this guy, but you looked at total magnetization, that will also satisfy this property. Okay. Similarly, now this is some terminology which I don't like particularly, but anyway, it's there in the field. If you look at something called a bilocal operator, which is basically a product of two local operators, this thing will also do that. Okay? In fact, many important experimental quantities are bilocal operators. Let me give you an example. Suppose you go to neutron scattering, right? And you measure what is known as spin structure factor. Now, spin structure factor looks like this. There's some momentum, right? Right? So you see, this I and j can of course be nearest neighbors, but they can be in principle distant from each other as well. Because when you do this sum, there's a free sum on I and a free sum on j, right? So there's no restriction on the inter-site spacing here, right? So these are examples of bilocal operators, okay, and similarly others. So given a Hilbert space, you can actually define an exponentially large number of, so given a Hilbert space of dimension n, given a system of n degrees of freedom, you can actually think of an exponentially large number of Hermitian operators, but not all Hermitian operators will thermalize. Okay? Only a polynomial class of Hermitian operators will thermalize, and basically these are objects which have this sense of locality. Now there's a simple way of thinking about it, which is that suppose you want to teach your computer how to solve this complicated quantum mechanics problem. In the sense that you want your computer to know how to write an exact diagonalization algorithm, right? Then, of course, what you need to do is you need to choose a computational basis, some natural computational basis. In your computational basis, so for example, if you have a spin half problem, a natural computational basis is you just specify what is sigma 1z, sigma 2z. These are just the Pauli matrices. Sigma nz, right? So this is some reasonable computational basis, right? So in this computational basis, you write your state. Now, if you think about these operators, yeah.
Why these properties are restricted to multi-local operators?
No, they can be tri-local as well. I just wanted to end somewhere. They can be, well, of course, tri-local operators are even harder to measure experimentally. But if you are a true blue theorist, tri-local is also fine.
So product of any numbers of operators?
Any finite.
Any finite?
Yes. But yeah, but you see, I mean, most useful operators are sort of this or whatever. That's all. That's why I stopped. So if you measure some very complicated string operators, they won't thermalize. Okay?
So bilocal just means that you take two local, product of two local operators.
Exactly. Which are, yeah. So actually at the end of the day, it's just related to the thermalization of a patch due to the rest of the system. That's the heart of it. Okay, see, if there's a string of operators here, you cannot think of this process as thermalization of this patch and thermalization of this patch. That's the point. Because if there's a long string here, everything has to thermalize, but then this patch might be extremely large. And the rest of the system might not act as a bath for it. That's roughly the intuition. Somebody had a question? 2 questions, so maybe you go first.
Does it have to be finite or can it be like density 0? Maybe take finite.
What has to be finite?
I mean, finite number of operators or just density? Take the
Finite. But we are going to extremely abstruse mathematical territories, right? As I said in answer to Zahid's question, most reasonable operators in quantum mechanics, which you're familiar with from your textbooks, fall in this class or whatever. So if you concentrate your life thinking about these operators, you'll already be in a good shape. But yeah, strictly speaking, finite. Yes, somebody else had a question, yeah.
Yeah, so in your third point, the energy of the initial state is extensive.
Yes.
In end. Because of that, the relaxation time is order 1. Otherwise, if we had an intensive energy, like a constant energy, then the time scale will also scale your degree of.
No, that's not quite right. Of course, the time scale of relaxation is a function of what energy you're looking at. That is correct. But okay, let me answer this question in this way. So suppose you have a spectrum. This is energy. So you see, in this spectrum, if you sort of, okay, I should have used some different color. If you sort of count the number of states here in some closed neighborhood of delta and try to calculate the entropy, then the entropy is a finite number here. That's because there's a exponentially small density of states here. Exponentially small level spacing here. Okay, and of course, this entropy goes to 0 as you approach the ground state and goes to 0 as you approach the highest excited state, right? But everywhere else, it's sort of non-zero. So unless you're really taking an eigenstate in a finite system, which is really the ground state or some very close by state, or taking an eigenstate which is really the highest excited state or some very close by state, this picture is right. So for those states, this thing would be true. this thing would be true.
So any bulk energy.
Exactly, exactly. So as you enlarge your system in the sense of adding number of degrees of freedom, the number of these kinds of eigenstates actually becomes really subdominant. Of course, these are very important for us when we do low temperature physics, because temperature naturally tells us to sort of start filling these states first. But when we are thinking of dynamics, they play a very subdominant role. Okay? There was some other question, yeah.
So suppose we have product of sigma is
Product of?
sigma is
On a string,
yeah.
that won't thermalize.
So why do we need this locality?
As I said, roughly speaking, this is related to the fact that if you have a really big system and you imagine a mental exercise of probing a small patch in that system, so S plus S bar is isolated. Okay, S plus S bar is isolated. So as long as this patch is finite, in the sense that this, as you double the system size, you should not double this patch. As long as this patch is finite, basically all that this is indicating is that this S bar can act as a heat bath for this S. That's what this is doing. Okay. When you have these string operators, if you again keep the extent of the string to be finite, that would also thermalize. But suppose you keep growing the string with the size of the system, that won't thermalize.
So they are saying there is no effective heat.
Exactly, there's no effective heat bath. That's the rough intuition here. Okay.
Also in this bilocal this thing, you keep the distance between the two patches the same while when you increase the system?
No, for example, in this example, the distance between these two bilocal operators is itself a fluctuating object. It can be extremely close or extremely far. But you see, you don't increase the size of these patches as you scale. Yeah, in that sense, it's a bilocal object. Yeah. And that is again connected to just this picture, because you see, all you're demanding is that this thing thermalizes and this thing thermalizes. Then the product also thermalizes, because in no way are you crucially using the information crucially that, you know, there are lots of operators here, and so non-commutativity of quantum mechanics is a crucial problem. You see, it's just connected to that. Okay?
You don't scale with n, but scale with a smaller power than that.
Okay, maybe something happens. I haven't thought of those somewhat weird situations. Yeah. Anyway, but let's keep our goals modest when we learn something. This is already good enough. Okay? Let's not try to, yeah, I mean, I hope you understand that this and this are already covering some fairly important operators that you have encountered, right? Yeah, I agree that there are all kinds of subtleties about taking limits, but let's not go into that right now, okay? So, yeah. Good. So now I spent more time on this than I wanted to, but that's okay. We had some discussion. So now let me be a bit quick. This probably Leah had done. So the natural way of understanding this dynamics, which was there, but of course, hopefully you remember it, that picture, is to expand the state, initial state, in terms of your energy eigenstates. Okay? But this is an extremely complicated exercise to do, because this is a many-body system. To find the energy eigenstates is very complicated. But let's say you do that. Then you can obviously write this quantity as two parts, one which is clearly independent of time and the other which depends on time. This star okay, so let's call it O alpha beta and let's call it O alpha alpha. Sorry, I wanted to make a point about the computational basis and these operators, and I forgot to make it during the question answers. So basically, if you take any such operator and you write it, this operator, in your computational basis, right? So you have some representation like this. You express this operator as some whatever, L cross L matrix or whatever in this representation. You would find that for these operators, the matrix representation would be very sparse. So most of the matrix elements would be identically 0. Whereas for these weird string operators which don't thermalize, the matrix representation would be highly non-sparse. So that's one computational way of thinking about it. Okay? So I can give you an operator which never thermalizes. For example, take this operator. You just take two eigenstates and you form an operator like this, just this operator. This operator would never thermalize. You can show it just by just plugging it in these equations, right? Basically what you'll get is some, and then let's say you start from some initial state which just has support here, then you'll get something like this. It'll never thermalize, it'll just keep oscillating, okay? So, correct, it's a highly non-local operator, and in fact the easiest way to see that is if you expand it, if you write it in your computational basis, it's extremely non-sparse. That's actually the correct physical way of thinking about it. Okay, so why does sparsity and non-sparsity come in the picture? One quick thing to just make it a bit more intuitive for you. Suppose in your computational basis you're trying to fill up entries. How do you fill up entries? You start from a state which is in your computational basis. You hit the operator on that state and you see to which other states it goes to. And those objects you make non-zero with the right amplitudes, and the other things you make 0. That's how you do it in quantum mechanics. If something is a local operator, at best, if you hit it with a state, it can only go to a reasonably small finite number of states, right? But if something is a much more complicated string operator, it can proliferate to a larger number of states. That's the intuition, okay? Good. Okay, so now comes the important point. From this equation, which is always true, this equation is always true, this is true from quantum mechanics, if we have to demand that, where is that picture? If we have to demand that that thing holds for all these class of initial states, then one simple way of doing it, it may not be the only way of doing it, but one simple way of doing it is the following. Oh, I have completed the loop. Okay, good. One simple way of doing it is, so there's a statement about matrix elements now, and it's a statistical statement. Okay, it's a statistical statement. So this is a statistical statement. What that means is that there can be exceptions to this statement, but the exceptions have vanishing probability as you increase your system size. So it's a statistical statement. E is basically the energy associated to this E alpha. So I'm now making a statement about these matrix elements. Where this epsilon is a very small number. So actually in practice this epsilon goes like this. So this is the thermodynamic entropy at that temperature. So it's an extensive variable. So it's e to the minus n by 2, order n by 2. So it's a very small number. Okay, and actually, if you think in terms of the dimensionality of your Hilbert space, let's say that's curly d, then this thing scales as 1 by square root d. Okay. Maybe you have encountered this statement in Leah's lecture. I don't know. Maybe not. Or maybe in a slightly different way. Okay. So if this happens, then that top picture is guaranteed. Okay. Now, there's one important thing to note here. That is,
Can you like explain this, what this means? Ambiguity concept.
oh, okay, maybe I'll draw a picture for you. Yeah, it means whatever I've written here.
First one is saying that the diagonal entries are all very close by, is it?
Not just that, more than that. Let me draw a picture here. It's hard for me to draw the picture for the, okay, anyway, let me just, oh, I can use this board as well, right? And the next one, wow. Okay, so let me use this one. Why should I erase anything? Of course, I'll just, okay. Of course, I'll confuse myself endlessly by switching between boards, but that's okay.
Oh, the third one.
Only these two, okay, yeah, fine. Okay, where was I? That one. So let me draw a picture for you guys. So suppose you write a computer program for some spin half problem with, let's say, 20 spins or something, right? With modern computers, you can reasonably easily do that. And you get all the eigenstates, and let's say you compute some local observable in all these eigenstates, right? And you just plot them. Then, basically, the answers would look like this, if you literally plot them. I mean, okay, this is going too slow, I'll just do this. So it'll look like this with some scatter, which will increase near the wings. Wings meaning the upper and the lower edge of the spectrum. And that's how this will look. Okay? Now, if you double your system size, then you will see that this fluctuation about this thermal answer. So this pink curve is a separate calculation. It's a completely separate calculation. It's the statmic calculation in which you just say, oh, I have a given temperature, and associated to that temperature, I just calculate my thermal answer and I just plot that curve. That's a completely different calculation. Okay?
So you do the microcanonical calculation.
No, you do the canonical one. So the map is this. So actually, it doesn't really matter because these are short-range interacting systems. So ultimately, it'll all be equivalent. But really, the map is that given an energy eigenstate, you transform it into the appropriate temperature. Yeah, because temperature is just a Lagrange multiplier to fix the average energy. Okay. Anyway, so now suppose you double the system size, you will see that again there is a scatter around this, if you wish, master curve, but the scatter would be much more decreased. In fact, how does the scattering decrease? How does the scattering decrease? It decreases like this. That's why exact diagonalization is a powerful tool for looking into these things. Because suppose you increase the number of spins from 10 to 20. You have just increased it from 10 to 20. But your Hilbert space increases from 2 raised to the power 10 to 2 raised to the power 20. That's a very important point. That's why, even through modest computer programs and stuff like that, you can appreciate many of these things. Yeah?
We are saying if these two hold, then our ETH hypothesis.
Exactly. Also, if you look at the off-diagonal matrix elements, most of them would be extremely small. Okay? Some of them would be not so small, but as you increase your system size, the probability of those outliers would decrease extremely fast. So these are all statistical statements. You can appreciate it from this plot. See, they are not really holding up here. They're scattered around this thing, but the scatter keeps decreasing as you increase your system size. Okay.
For this, you need the matrix is sparse.
Yeah.
But not in a eigenstate basis.
No.
But this assumes that the eigenstate.
In my computational basis. Right, exactly. That's a good point, thank you. So in fact, this thing comes from a sum rule, and basically to cut the story short, you're absolutely correct. If you assume your high energy states are delocalized, there's a natural way of seeing this. Right, but you see when I said local sparse, I was talking about the computational basis, which is some unentangled basis or very simple basis. I was not talking about the eigenbasis. Yeah. But these statements are for the eigenbasis. The operator O, local operator O, expressed in the eigenbasis. Yeah. Okay? Yeah. Yes?
How do you construct this pink line that you have drawn?
Oh, as I said, so let's just do it. So suppose you do exact diagonalization, right? Whatever, you get some energy eigenvalues, right? You just do this. Trace of O e to the minus beta h, trace of e to the minus beta h. That's what you do. That's the canonical answer. I forgot. Yeah, sorry. That's the canonical answer, right?
Beta is fixed by the value of n.
For this calculation, you just take your temperature to be from whatever. Temperature can be a negative number also for a bounded spectrum. So
No, beta has to be fixed by the energy value.
no, but when you're plotting this graph, you're of course changing beta.
No, at a given energy.
That's correct. But in your computer program, you don't think like that. You just do it for all possible beta and just draw the graph. For all possible.
If I don't have a computer, then what I do is that I fix my energy value, and I do have a computer. Okay, you seem to be lost. Okay.
No, even if you don't have a computer, you do whatever calculation you want to do and just repeat it n times. Okay?
I was saying that at a given energy.
Yeah, of course.
The value of beta.
Yeah, that's correct.
That the energy value is what I.
Absolutely. Because beta is just the Lagrange multiplier which fixes that average energy. That's it. Yeah, correct. Absolutely. Yeah. Right. All of us have computers. We have our cell phones. But anyway, I mean, yeah. In a practical setup, this is what you do. Good. Now, you might think that why am I making a big deal about this statistical statement and what is happening here? So actually, so I haven't told you what this eigenstate thermalization hypothesis is. Let me not go into that right now. What I've told you is that there is this thing which ensures this, which ensures the top picture. Now there is unfortunately no analytic proof for this thing, for this ETH. But there is a situation in which there is an analytic proof in a completely different context, which is known as random matrix theory, which probably Leah has discussed in reasonable detail. Let me just discuss it in 1 minute in my own way, just to set up notation. So suppose you take a very large matrix, again some curly D cross curly D matrix, which is a random matrix. How do you generate this random matrix? It's very easy. So what you do is, let's say you take a matrix A. For each of its entries, you just throw let's say in the simplest version, you just throw a random number generator with a Gaussian probability distribution of mean 0 and variance 1. That's called the normal distribution. Let's say you just throw these random numbers independently here, 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 here. So you fill up the entire matrix. Okay, good. Then once you get that matrix, you just do this A plus A transpose by 2. Just to make sure that this becomes Hermitian and all that. Okay, and that resulting matrix is one particular realization of what is known as ensemble of Gaussian orthogonal. I already said ensemble before. Anyway, it's a GOE matrix. Yeah, it's a GOE matrix. Okay. For this particular matrix, remember there's only one matrix. Okay, which I have produced through some probabilistic process. For this particular matrix, if you look at any operator O, any Hermitian operator O, so in random matrix theory, I don't have a restriction for locality and stuff like that. If you look at any operator O, it'll satisfy the following equation. Oh, sorry. Oh, this happens, okay. It will again satisfy these two equations, okay? And this you can analytically prove, okay? But these equations look interesting, so let me write it here. So in random matrix theory, in RMT, this O is a general Hermitian matrix. And these are some pseudo-random number variables, which again look like they have a normal distribution with mean 0 and variance 1. So this O bar is trace of O by D, and this O square bar is trace of O square by D. Okay. This result you can give a reasonable proof for. On the other hand, if you have a local Hamiltonian like there, if you have a local Hamiltonian like there, in that case, you have a bit more structure here in the sense that some constant functions here are replaced by some more non-trivial functions. Okay, see, this is a constant function, some number. This is also a constant function, it's some other number. These constant functions are replaced by some more non-trivial functions. Okay? This is the thermodynamic entropy. This some envelope function. These are again some pseudo-random number variables times 1 minus delta. Okay? So this is RMT and this is ETH. Okay? Now actually it's very important that both this and this happen together, or in other words, both this and this happen together, because otherwise you can land up in perverse situations where your final time dependent answer can keep oscillating in some complicated way. Here I'm just drawing some simple oscillation about some thermal answer. But you don't want that. You actually want it to go to the thermal answer, right? So both these properties should happen together to ensure that there is some sense of thermalization. Okay? Good. But let me point out one thing very quickly, which is in the random matrix theory approach, if you want to think of the random matrix as a Hamiltonian, after all, it's some Hermitian matrix. So by some change of your thought process, you can just think of it as arising from some random matrix, from some Hamiltonian, right? Basically, that Hamiltonian would be a highly non-sparse matrix. So if you try to write that Hamiltonian in real space, it would not look anything like a short-range Hamiltonian. Okay? So in random matrix theory, basically you lose this notion of locality. Okay? Now, when I introduce Floquet ETH to you, you will see that it's somewhere, it's almost halfway between these two things. Okay, it's halfway between this and that, and we'll see that. Okay.
So then it's quite remarkable. On one hand, you have something which is local and for which ETH works, and
Yes.
on the other hand, you have something which is not local,
Yes.
and yet you have a similar result.
In the Floquet thing.
Here?
No, I mean, to me, this is far easier to understand than this.
No, but then how do you draw a parallel? Because the second one.
No, I drew this parallel to be provocative. It's a parallel. It's not a mathematical, you see what I'm trying to say? I'm just, but there would be some sense of truth in this parallel. Because, okay, I can think of a Hamiltonian which generates a Hermitian matrix. If you really think like that, then it is true that that Hamiltonian in a RMT setup would be completely non-local. It's completely true, right? So in that sense, something in the ETH thing breaks down, right? But it's still, it's interesting that from that viewpoint, it still gives you some equation like this. So it's interesting. So actually, when I introduce Floquet ETH to you, then probably you will be able to see how it comes up and where this non-locality comes up in, right? Yeah. Yeah, so this, yeah. So I made this point like precisely to sort of tell you guys that maybe there are some hidden connections which are not yet well posed. Yeah. So it's meant to be provocative, and maybe somebody will make that hidden connection properly. Yeah. Oh, sorry. What should I do? Any questions till this point? Yeah, I'll discuss that. But any question till this point? I haven't yet introduced Floquet ETH. Sorry, you were saying something?
You will introduce why it will come.
Well, we'll see about the why, but I'll introduce it, yes.
Yeah, you said that this R alpha beta or Rn, they are pseudo-random variables. So are there like weak correlations among them?
Yeah, there are weak correlations among them. And I don't know, okay, so one way, so there's a very nice paper by Shrednicki recently, maybe in the last 2 years or so, where he discusses that these weak correlations are really needed if you want to understand some properties of certain things which are known as out-of-time functions, OTOCs, okay? But I won't discuss it. Maybe somebody else will discuss it here. I don't know, yeah. But there's a very nice paper by Shrednicki on this. But at the level of expectation values, you can almost forget about these weak correlations. But if you calculate these other slightly more weird objects, OTOCs, then somehow it plays a very crucial role. Yeah. You get some, yeah, if you don't introduce weak correlations between these pseudo-random numbers, then you get some things which should not happen. Yeah.
In both cases, the off-diagonal elements are extremely small.
Exactly, in both cases.
So, but then physically, what would be the difference then between the two? Because you made a clear distinction.
Yeah, there's a big difference between the two in the sense that here, modulo this RMN. So maybe if you normalize your variables in such a way that suppose you sort of mod out this RMN piece, modulo this piece, this is a constant function. But here, this thing has a lot of structure. This f function here has a lot of structure. I mean, it's some non-trivial function. So if you hold this E fixed and just plot it as a function of omega, this function really has some very non-trivial shape. And this shape gives you a non-trivial relaxation to equilibrium. So basically, this f function explains that relaxation, which I was talking about from different initial states. But that is because your Hamiltonian is local and there are all kinds of energy transfer processes which make a non-trivial relaxation. For the random matrix theory, it's just some constant number there. So that's one of the important differences. Yeah.
So this omega is the gap, huh? You did not define.
Oh, I did not, sorry. So this omega, so this is an off-diagonal matrix element, right? So there's a E alpha on one side and there's a E beta on the other side. This omega is basically E alpha minus E beta. Okay, and this E bar is of course the center of mass. It's like E alpha plus E beta by 2. Okay, right.
What is R alpha beta? Some.
Here, so as I said, yeah, this is the most difficult part. So if you, again, Shamik would not like it, but suppose you sit on your computer and you, but maybe you never sit on it. No, yeah, that's correct. Yeah, that's correct. Thank you for correcting my English there. That's correct. But jokes apart, when you actually look at the off-diagonal matrix elements, you will see that they are fluctuating in signs as well. Okay, so these R alpha betas actually incorporate these sign fluctuations. Okay, so this is slightly more detailed. There is a way of plotting these things properly, and there are some very nice papers by David Lewitz on this, which you can look up. So if you plot these things correctly, you will see that this fluctuating part can be represented as basically a random number generator whose mean is 0 and whose variance is 1, right? Because it then incorporates these sign fluctuations correctly. So it can be thought of as a random number. Yeah.
Omega should have an index.
Index. No, omega is just this. Oh, if you want, I can place it. Yeah, if you want. No, of course not. But I think it's clear from the situation what we are trying to do. Yeah, of course. Good. Any other questions? Okay. So now let's come to Floquet and so in Floquet, there are some superficial similarities to the undriven problem. So what does that mean? So of course you have this. And now let's say you again look at the unitary evolution. In particular, let's say you look at the unitary evolution for one full cycle or one full period of whatever parameter you are driving in time. Okay, then that, as we already discussed, looks like this. Okay, and this can of course be notationally written like this, notationally. Because this is a unitary matrix, you can write it as an exponential of a Hermitian operator like this. So just to set terminology, this thing in the literature is called Floquet unitary, and this thing in the literature is called Floquet Hamiltonian. Okay. Now, suppose you are just looking at stroboscopic dynamics. What that means is, suppose you are not looking at all possible values of time, but let's say you're only looking at time intervals like 0, capital T, capital 2T, 3T, and so on, right? Then you see, if you have information about this guy, then in principle you can just write a equation like this, raised to the power n psi 0, where n is 0, 1, 2, and so on. But now, using that equation, this thing just becomes psi 0, right? So for stroboscopic dynamics, it seems that I can get away by thinking of a unitary driving process with the Hamiltonian HF, where the only restriction is that time is an integer multiples of capital T, right? So that is the superficial similarity with undriven problem. So I would say this is a superficial similarity. And I'll explain why this is superficial. But I hope everybody agrees with me. This is very simple algebra. Okay. Now again, as we did in the undriven problem, to write this in a slightly better manner, maybe it's good to look at the eigenvalues and the eigenvectors of this unitary matrix U cycle, right? This is this Floquet unitary matrix, right? So actually, I'll just introduce some more notation. So let me just call U cycle to be UF, because in the literature it's normally denoted by this language. So let me just call it UF. So this UF, I'll just expand in its eigenbasis now. The crucial thing is, the eigenvalues now live on a unit circle, because these are the eigenvalues of a unitary matrix. These are not the eigenvalues of a Hermitian matrix. Okay, so this is the decomposition of this thing in terms of its eigenvectors and eigenvalues. So then from here, if you want to write the Floquet Hamiltonian, you can of course formally write it. Sorry, let me put in where this thing is related to this thing. But you see there's an ambiguity here already, because this Floquet Hamiltonian is some operator which only generates the correct temporal evolution at n equal to 0, 1, 2, 3 and so on, right? So there's an ambiguity here. So the ambiguity is that ENs can be shifted by, any of these ENs can be shifted by an amount in h bar omega d, where omega d is basically 2 pi by t. Okay. So basically there's an ambiguity in this Floquet Hamiltonian. So strictly speaking, HF is ill-defined. Of course, the operator UF is completely precisely defined. There's no ambiguity here, but there is an ambiguity in defining HF. Okay. Sorry. So again, if you look at these eigenvalues, these guys, they actually live on some unit circle, and again they have some interesting distribution. They have some interesting distribution. In particular, for a general interacting system, two eigenvalues cannot come arbitrarily close to each other. That's this notion of level repulsion, which must have been introduced to you earlier, right? So again here, this notion comes. Okay, so what is Floquet ETH here? So again, Floquet ETH is you look at some local operator and you look at the matrix elements of that local operator in this basis. So the diagonal matrix elements are of course denoted by this, and the off-diagonal matrix elements are denoted by that. Okay? Then you see a very interesting statement. What should happen in a large system is the following. This part looks like RMT. But there's again an f function which depends on that specific operator. Sorry, let me. And there's again some pseudo-random number variables. So you see, this is the form that is expected. Now, let's stare at this and let's try to see. So one thing you will immediately appreciate here is that unlike in ETH, if you remember, let me use some different color. In ETH, if you remember, here there was okay, and in ETH, if you remember, here, oh sorry, of course there is, there's square root t, of course, yeah. So I should use this thing. In ETH here, it was sorry, I'll put the brackets downstairs, or maybe I'll just. Yeah, this is what was there in ETH. In Floquet ETH, this energy goes out of the window. There's no energy in this equation. Now, this is easy to appreciate. this is a periodically driven system. So of course, energy is not a conserved quantity. So it should not appear in any important way in any of these matrix equations, right? So let's look at this. So the way through which energy goes out of the window here is the following. In the canonical ensemble, the distribution is weighted by e to the minus beta times e, beta times h rather. So the simplest way of making energy go to 0 is put beta equal to 0, right? So that's what you do here. Here, the way energy goes out of the window is that you cannot have a non-trivial dependence like this. Instead, you just have a dependence 1 by square root d, right? Because that has the same scaling as this kind of an object. And the second place where the energy dependence is here. This is e bar comma omega. But now this object, this f function, is just a function of omega. So what is this omega? This omega is just this, right? It's just this, okay?
The diagonal entries are decreasing faster than the octagonal entries, which is kind of...
No, what do you mean it's decreasing faster
because
than?
it is 1 by t and this...
No, but there's a trace upstairs. It's just, yeah, so trace is a sum over d number of expectation values again, right? Yeah, it's order 1. For reasonable operators, it's order 1. Okay? Good.
Are you going to comment on if the form of f?
Okay, that's a good point. Since you asked, let me make a comment. And this is again for young people like you guys. So off-diagonal eigenstate thermalization hypothesis is very well studied in the undriven case. Off-diagonal Floquet ETH is not at all well studied. Okay? So let me make a provocative conjecture here, even though I'm being recorded. So anyway, this is a conjecture, so you can try to prove or disprove it. So suppose you have this omega d, and you go to the low frequency limit, then the claim is that this thing will also go to a constant function so that everything agrees to RMT. But please bear in mind that this is a conjecture. I'm just making a statement from some gut feeling, but yeah. But anyway, the key point is this is not so well explored or understood in driven problems. So it's an interesting thing, yeah. Okay. So now let me search for this. Oh yeah, it's here. That's good. That's very good. Now remember the computer exercise we did for generating this plot. Now let's do a similar computational exercise to generate the eigenstates of the Floquet problem. I'll in fact explicitly give you a simple strategy to do that very soon. But let's say you somehow get the eigenstates of the Floquet operator, and you calculate the expectation value of this operator. Then you actually, can someone guess how this graph will look like? I mean, there's only one thing that this graph can do. Here it has this non-trivial shape as a function of energy, but there, I mean, okay, you can try to plot it as a function of quasi-energy by just restricting everything to minus pi by t to pi by t, right? Just to ensure that it's some periodic function and whatever, right? But anyway, what it'll look like is, it'll just have a scatter around a constant. Like this, okay? So this non-trivial dependence on energy would be gone, and it'll be replaced by something like this. And of course, it'll intersect this curve at the place where beta is 0, okay? Now there are two other points here. I told you that when you do this numerical exercise, there are more fluctuations near the wings. But if you look at this plot, then there'll be no such effect. I mean, there would be no wings, essentially. But that is simply because in this earlier problem, in the undriven problem, there is a precise notion of what is low energy and what is high energy. Whereas in a Floquet problem, there is no notion of low or high energy, right? I mean, because energy is not strictly defined, right? It's just defined modulo some 2 pi by t, right? So, yeah. Okay. So there's this really nice paper, which I'll recommend you guys to read if you want to implement this thing on a computer and check that this is happening. So let me just write the reference here. ERE 90 052105 2014. Okay. So yeah, so in this paper, let me erase this now.
Energy earlier. Now it will be eigenvalues of the Numerical ETH, right?
If you want, you can make it eigenvalues of the Floquet Hamiltonian as well, but then you have to somehow fold everything to be in minus pi by t to pi by t. Yeah. I mean, the best way to draw it is really on a unit circle, but if you want, you can take this particular Brillouin zone approach. Yeah. So where is it? In this paper, they looked at both the undriven and the driven problem, and they considered this Hamiltonian. This is a very famous model in 1D quantum magnetism, okay? And in particular, they took some 3 numbers for G, H, and J, which were all simultaneously order 1, because they wanted what is known as a non-integrable quantumizing model. So I don't know, do people know if, suppose I put certain terms to be 0 here, then ETH should break down. And do you know why? Have people encountered this already? This kind of a problem? Some people have encountered it, I know that, but I don't know about the majority. Have they encountered it?
No, the question is what is that limit?
Yeah, I don't know who has discussed it. Thousands of people may have discussed it. But what I'm asking is, this problem, this is a very well-known problem, and it's what is also known as again, I haven't defined this really, but maybe you have been introduced to these things earlier. This is what is known as a generic non-integrable spin chain, right? What I'm asking is, if some couplings are made 0, then does it become integrable? Do you know? Of course, one simple thing is put J equal to 0. That's obvious.
If H equal to 0, it becomes a bigger.
Yeah, and why do you say that?
Because it's a transversizing model. Transversizing model can be exactly so.
Okay, good. So you have familiarity with this, right? Okay, that's very good. So yeah, so in this paper, these authors took all 3 numbers to be order 1 so that they are far away from this integrable limit. In fact, this is how they generate the Floquet unitary. And they take a particular tau, which is also order 1. In fact, they take 1.6 to be precise. So what is this Floquet unitary? So basically what you're doing is, you have this Hamiltonian, and for a time window of tau by 2, you only have the z parts as non-zero, and for the rest of the time, tau by 2, you only have the x part to be non-zero. in your Hamiltonian. And this just keeps happening back and forth, right? And using this, they generate this Floquet unitary, and they also look at its eigenspectrum and its properties. And they indeed find that Floquet thermalization seems to happen faster than in the undriven case for the reasons that I have explained.
What are the subscripts that you use for H?
Here. So this HX, yeah. So this just signifies that the Z terms are on here for the period Taiboid 2, and this signifies that only the X terms are on here. Okay, right. Okay, and I really encourage you to look at this paper. I see that I'm running out of time, so I think I'll continue next time. And next time, I'll just provide you with some rationalization of this result why it goes to a constant, but it will be at best a rationalization. Because again, I would like to point out, especially to this audience, that there is no proof for this statement, and it will be very interesting and important to try to think along those lines. But I'll just give you some hand-wavy arguments. But you should always remember that those are hand-wavy arguments, and there might be several subtleties hidden in those arguments. Okay? So I think this is a good point to stop, and maybe I'll take questions if there are any.
Okay, so are there any questions left? Okay, if not, so let us thank Arnab for the talk.